Hi everyone, welcome back. We're now getting into chapter 13, which is about curves in space, also known as space curves. We did look at one kind of curve in space back in chapter 12, and that was the notion of a line in space. And we looked at how to represent a line by a vector equation or by parametric equations. We're going to take these ideas now and extend them to general curves in space. This is as opposed to chapter 14. Chapter 14 we will get into surfaces in 3 dimensions, of which in chapter 12 we looked at the plane, for example. Plane is a surface in 3 dimensions. We will look at in chapter 14 more general surfaces in 3 dimensions. The fundamental tools we will use, though, to understand curves and surfaces in space will be lines and planes, because this is what we get when we take a curvy object and approximate it by a flat or a straight object. So with calculus, we will be studying curvy things by approximating them with lines and planes. Alright, let's have a look at the first motivating problem. Let's describe the motion of the particle whose coordinates at time t are given by x equals cos of t, y equals 0, z equals sine of t. First thing to note here is that x squared plus z squared is equal to 1. That's cos squared plus sine squared. So this is a circle. And we also have that y is equal to 0. So it's a circle in the xz plane. And so let's just get our coordinate axes sketched. There's our x-axis, there's our z-axis, our y is coming out this way. And what we have is a circle. In this case it's a circle of radius 1. And as t increases, when t is equal to 0, we're at x equals 1 and z equals 0. And then as t increases, we go around the circle in this direction. And so that is what the path our particle is taking as t increases. Now, in general, such a set of equations, so x is a function of t, y is a function of t, and z is a function of t, this is called a parametrized curve or a parametric curve. And it's given by 3 functions, each a function of t, each one of them telling us how the corresponding variable changes over time. So x is f of t, y is g of t, and z is h of t. T is called the parameter of this parametric curve. We can go one step further. So we can bring vectors into the mix in the following way. Let's suppose we look at the set of all points as t ranges over its domain. Then what we get is set of all points determined by the parametric equations gives us some sort of curve. For a given point along that curve, we can describe it by using its position vector. Its position vector would be r of t, and that gives us the position of this point, x of t, the position vector for this point, x of t, y of t, z of t. So here we are thinking of the triple as both representing the coordinates of the point, but also as the components of the position vector for that point. If we take that little change in perspective, then what that means is we can talk about the curves as the collection of points now as a curve is made up from a vector valued function. So for any given value t, r of t produces a vector at a given time, and that's the position vector for a point. So for example, let's describe the motion of the particle whose position vector at any given time t is given by r of t is cos of t, sine of t, and t. So if we wanted to use our angle bracket notation, this would be cos of t, sine of t, and t. And again, what we get here is that x squared plus y squared is equal to 1. So this is in some sense circular in nature in the x and y coordinates, but the z value is increasing as t increases. So we get, in this case, let's maybe start at when t is equal to 0, we're out here at the point x equals 1, y equals 0, and z is equal to 0. But then as t increases, the points then start to spiral around the z-axis. And this is because the path of the particle circles around the z-axis. And the z value increases. As t increases, because z is just equal to t. And so this curve actually has a special name. This is called a helix. Now let's see how we can actually use math3d.org to plot such curves. So when we first encounter math3d.org, we again have this example of a surface already drawn. Let's close it out. In this case, we're going to add a parametric curve. We've done this in the past in chapter 12 with lines. Now we're going to do it with just any function for the x, y, and z components. In this case, the example that comes up has x equals cos of t, y equals sine of t, and z equals t, so it already is that example we wanted, and there is the helix that we had sketched in our notes. It's circling around the z-axis, and as t increases, it's going up the z-axis. So what we've just done here is we've introduced this idea of a vector-valued function. It's a function that associates with a real number input, given by t, an output, r of t, which is a vector. So we call this a vector-valued function. In this case, we can write it as r, and then the colon indicates that this next set I'm putting here is going to be the domain. So what does r take on? It takes on real numbers as input, and what does it give as output? It gives three-dimensional vectors. So we can denote those as v sub 3. That's what our textbook does. And v sub 3, it's just the set of three-dimensional vectors where x, y, and z are in R. So that's what a vector value function is. Real number in, vector coming out. What this means is we can describe a vector valued function just by three functions of a single variable in with a single value coming out. That's f, g, and h. So f is our function that determines how the x-coordinate changes over time, g is how the y component changes over time, and h is how the z component changes over time. We could ask things like, what is the limit as t goes to a particular value? What does the limiting value of the vectors go to? And those are just computed by doing the individual limits of the component functions, which are just functions of a single variable, so those are back down to calculus 1 limits, 3 of them, 1 for each component. We say that a vector valued function is continuous at a point A, provided the limiting value of the function is equal to the function value at that point. So the limit of r as t goes to a is exactly r of a. What we get from this and the line above is that r is continuous as a vector valued function if and only if f, g, and h are continuous as functions of a single variable. And so now let's have a look at an example. We're going to find the vector equation and parametric equation for the line segment that joins these 2 points. So we've got our point P, our point Q, and what we're interested in is parametrizing the line segment between them. So the first thing we're going to note is that we can find a vector in the direction of this line segment. It's going to be given by that vector P to Q. And so the vector from P to Q is tip minus tail, so it would be 4, 1, 7, minus 1, negative 1, 2, which is 3, 2, and 5. Now that gives us our vector. I'll write that in here as a vector from P to Q. We're interested in describing all points starting at P and ending at Q. How do we do that? Well, this is given by the vector equation where we construct that line. So we'll construct a line just as we did in chapter 12 as a vector equation. It is the point we're starting at, which is our point P. And then we'll add to that any multiple of the vector in the direction of that line. So that is our vector v, and this is our point P. However, in this case, we only want the points between P and Q. So how do we get those points? Well, we restrict t. When t equals 0, that gives us our point P. As we can just see, plugging in 0, 0 times the vector v gives us just our point P. And then as we add multiples of our vector v between 0 and 1, so t taking values between 0 and 1, we get all of the points on the line segment up till finally that last one when t is equal to 1. So this first point is when t is equal to 0. So that means our vector equation for the line segment is 1 plus 3t, negative 1 plus 2t, and 2 plus 5t, where t ranges over the values from 0 to 1. So there's our vector equation. We can also write down parametric equations, and that is just grab the corresponding component. So parametric equation is x equals 1 plus 3t, y is equal to negative 1 plus 2t, and z is equal to 2 plus 5t. And again, t is ranging over the values from 0 to 1. So let's see how this looks in math3d.org. How can we plot this? So we'll go ahead and use the curve that we've already plotted here, and we'll just change these. So the first component is 1 plus 3t. The second component is negative 1 plus 2t. And the last component is 2 plus 5t. And the thing to keep in mind is that we don't want t to range over arbitrary values. We want t to start at 0 and to end at 1. And so there's our line segment. And if we wanted to make sure it started and ended at the points that we wanted, we can go ahead and we can plot the point. We'll make this our point P, so I'll just label it P here. And what is P? P is 1, negative 1, 2. So we got 1, negative 1, and 2. We can see that's exactly where our line segment is starting. And then we'll plot the next point. This is point Q, which is 4, 1, 7. 4, 1, and 7. And that's exactly where our line segment ends. So there we go. We've constructed a line segment starting at one point and ending at another point, and we constructed it as a parametrized curve. Let's have a look at the last example. We want to find a vector function that represents the curve of intersection of these two surfaces. So we've got what we call a paraboloid, and we got our parabolic cylinder. So what do we want to do? Well, we want to find x, y, and z such that those are components of a point that live on both surfaces. So we need z to be equal to 4x squared plus y squared, and y is equal to x squared. Well, that means we need z equal to 4x squared, and if y is equal to x squared, then I can write this as x to the fourth, and y is equal to x squared. So I took the original two equations defining the two surfaces and said if any x, y, z value satisfies those two equations, they also have to satisfy these two equations. And vice versa, any x, y, and z that satisfies these two equations has to be on the intersection of the two surfaces above. But this is nice because it tells me that y is some function of x, z is a function of x, and x itself is a function of x. So the curve can be described by x is given by t, y is given by t squared, because y is equal to x squared, and z is equal to 4t squared plus t to the fourth. And here, t can be any real number. In terms of a vector equation, those are our parametrized equations. So our vector equation for the curve, we get that r of t is equal to t squared 4t squared plus t to the fourth, where t is any real number. And again, let's double check, make sure we got this correct. We can do that by constructing these curves and getting a visual for them. So I'll zero out the previous stuff. Now we'll go ahead and enter our curve in. So x is t, y is t squared, and z is 4t squared. Then I have to hit the right arrow button. Right now I'm caught in the exponent. I've hit the right arrow button. I'm now down below and on the regular line. So now I can do a plus t to the power of 4. And I'm going to let t be ranging over the values. Let's just go from -5 to 5. That will probably be enough to take us off the page. There we go. So there's our curve. I'm going to change its color to yellow. I'm going to bump up its width a little bit just so we can make it a little bit more visible, because what I'm going to do now is I'm going to say, well, this is the curve of intersection of those two surfaces. Let's plot those surfaces to see that this actually is the intersection curve. To plot the surfaces, the first surface is z equals 4x squared plus y squared. That's an explicit surface because z is explicitly written in terms of x and y. So when I type explicit surface, it gives me an example here. I can go ahead and change that. We want it to be 4x squared plus y squared. So there is that first surface. We can see it stops at y equals 2 and -2. We can bump those up a little bit. I'll go out to 5, -5, and 5. So there's our paraboloid. And let's do the next surface. We'll add one more surface. In this case, it's y equals x squared. That's not an explicit surface. Z is not written as an expression in terms of x and y. This is what we call an implicit surface, and that allows us to write out the full equation. So we've got y on one side of the equation, and that's equal to x squared on the other side. And we're interested in all points x, y, z that satisfy this equation. You can see that it's been plotted there. The z doesn't reach up as high as we want, so we can make it reach up quite a bit higher. Make it maybe go up to 10 or 15 or however high we want it to plot. So we've got those two surfaces plotted, and we can see that where those two surfaces intersect is precisely our yellow curve. It's the curve we plotted. So that yellow curve is the curve of intersection of these two surfaces. Alright, so that's it for this section. It was just a short introduction into vector valued functions and the plots of these vector valued functions, which are space curves. In the next section, we will start to get into the calculus of space curves. Thanks for watching, and we'll see you in the next section.